Okay, hello everybody. 4 weeks. We're almost there, and we're on the last project cycle, so that part should feel good. Um, I know the projects, by the nature of the class, get harder, and the data structures get harder. Um, and not having the live lab, I suspect, at least I know for me, and I suspect for some of you, makes this a harder task. So good on you for sticking with it and getting yourself right up now to the end. So last leg of this marathon, as it were. I had the schedule up because I wanted to show you I made an adjustment just to match reality over the weekend. So here we are on the week of May 5th. Um, so we have 3 weeks and then a project. Project 4 uses a binary search tree as a data structure. Project 3 used a doubly linked list as a data structure. Project 4 is a very similar project except for the data structure is new. So it's going to load a file, it's going to process commands, and then it's going to call functions inside of a binary search tree class this time instead of a doubly linked list class. So you can, if you want to, just get started right today spinning up um, some parts of Project 4. The other thing is that the labs should have you complete almost all of the supporting code in the data structure leading up to the project. So for the most part, if you apply yourselves well on the labs for the next 3 weeks, then you're going to have everything you need except for the driver for Project 4. So that's supposed to be the reward. Uh, yeah, it is still morning. Good morning, Davis. Um, it is still morning, isn't it? It's only 11 o'clock. I think I've been up since like 5 because we're having 100-degree weather right now, and I'd rather be up when the morning is a bit cooler. By the afternoon, you just want to hide inside. So good morning to you as well and to everyone else who's here. Okay, so hopefully that update helps on the project. The other thing about the schedule is um, the college has changed finals week so that we no longer have finals. We just have one more week of class. So I took away the special meeting time because we have to meet at the regular time on the week of May 26th. So we really have 4 weeks, but the last week is just a one-off lab that's meant to address something in the course outline. You're supposed to hear about hash tables in this class, so we're going to do that during the last week of meetings. But that said, I think that we're going to finish. Our last meeting should be May 26th as far as I know. So you will be done with the project by then, and then we'll come together one more time on May 26th. There's one last lab that has to do with hash tables, completely unconnected to Project 4, and then we're done. So I anticipate that we will have our last broadcast on May 26th, and then you'll have until the following Sunday to turn in that last lab. So that's what's going on. That's that small change. We're going to meet the regular time on Tuesday, May 26th at 11 a.m. And I anticipate that that'll be the last time that we'll need to meet online. Okay, so what we're working on this week is binary search tree. So I'm going to have to ask your indulgence to let me draw cruddy pictures. I got a drawing tablet, but I'm still working on trying to make pictures with it fast. I can go faster with paper, so for now I'm still sticking with the paper. Okay, so let me just. Why is this thing not alive? Okay, so let me just bring you up to speed in terms of the data structures that we've dealt with, and hopefully you remember array. So an array, we kind of picture the data being like this in an array. Sort of across one dimension, and of course we access the data with indexes. And arrays are quite nice because they allow what we'd call random access of data. And by random access, I mean I don't actually have to iterate across an array to get element 3. I just say array index 3 and I get this element. So I can just randomly jump into an array wherever I want, which is nice. We have a vector. Which is very much like an array. With indexes like an array. The difference is that vectors can be appended to and removed from. So I can make a vector grow with a pushback, and I can make a vector shrink with an erase function call. So vectors and arrays are very similar in the way that we can randomly access data, but vectors can grow and shrink, whereas arrays are always fixed size. Then we did linked list. So we did a singly linked list, the head pointer. We did a doubly linked list. I don't know what you think, but I think my drawing today kicks ass. I feel like I'm doing good drawing. So even if I'm not, you can pretend like I am and say that, yeah, those are great drawings. These are too close together, so that's a bummer. Anyway, so singly linked list, doubly linked list. So these do not allow random access, like vectors and arrays. If you want a piece of data, you have to iterate the singly linked list or the doubly linked list, right? So one difference between these linked lists and vectors and arrays is that they do not allow for random access. You actually have to basically use loops to iterate over them, to locate data, to insert in between them, to remove things. No random access. You start at one end or the other, and then you iterate them to get to the location or the piece of data that you want. But they do allow for dynamic sizing. So like a vector, they grow and shrink at will. So what I'm about to say you can't really see, but I will tell you that whenever you push back on a vector, that actually causes the computer to do a lot more work than whenever you push back on a doubly linked list. With a vector, since they're actually built on arrays, what a vector does when you add an element to it is that you make a brand new larger vector, and then you copy all the contents from the old vector into the new vector, and then insert the new piece of data. So every time you push back on a vector, you have to actually create a new slightly larger vector and then copy contents over. Whereas in a linked list, you just make a node and you tack it on. So linked lists are much better at the problem of dynamically adding data. They're much better for it. Vectors are actually pretty inefficient. Vectors are much better at that. Okay, so what we're adding today is called a binary search tree. It is dynamic. It does not have random access. So it has that same property where you're going to have to iterate the structure to find data. It is dynamic, so it's quite good at adding new data efficiently. Removing data sometimes can be a pain, but adding new data it's quite good at. The other thing that it has that none of these others has is that it is sorted by its nature. Binary search trees are always sorted. If you have something that looks like a tree that's not sorted, then you do not have a binary search tree. So one thing that binary search trees introduce that none of the other structures by default, just by the way they're built, is that they are sorted. Now we did look at a doubly linked list in a way to insert data to make it be sorted, but a binary search tree is by design always sorted. There is no option to not have a binary search tree be sorted. The reason why it's called a search tree is because search is allowed by the fact that the data is sorted. So we can easily search through a binary search tree because we know the data is always sorted in a binary search tree. Okay, no, so Davis asked, when you're resizing a vector, what happens to the old copy? It's actually deleted. So the memory for the old copy of the vector is ultimately deleted. It's underneath a vector. You can't see it when you're coding with it, but it's dynamic underneath, and it uses dynamic arrays to do that trick. So yeah, the old copy of the vector will get deleted when you upsize a vector. Okay, so binary search tree, they look like this, by the way. Kind of like a family tree. So conceptually, they look like this. The reason why we call them binary is because each node has two possible children. So in binary search tree terms, we can call some nodes parents and other nodes children. And the binary part means that each parent has at most two children. And notice, by the way, that you can have multiple generations. So a child can also be a parent, but never of anything more than two children. And these just grow and grow and grow. So the binary part means that each node has at most two children. You can have no children, by the way, or you can have one child, or you can have two children. The search part is making note of the fact that the data in a binary search tree is always sorted. It goes in sorted, it stays sorted. The tree part is because conceptually it looks like a tree, like a family tree, although it's upside down, right? Here's the bottom of the tree, but we usually draw it at the top, and then here's the branches coming out. So binary, two children. Search, they're all sorted. And then tree, because conceptually they look like a tree. All right, so that's the quick introduction to binary search tree. So we have the binary part. Now let me show you the search part better. When you create a binary search tree, the main node, the first node that goes into a binary search tree is called the root of the tree. So every binary search tree has one root, just like every singly linked list. I feel like I'm in an odd angle here. Whatever. A singly linked list has a head. A doubly linked list has a head and a tail. A binary search tree has a root. So the first node that goes into a binary search tree is called the root, and it will contain data. I'm just going to put 50 here for argument's sake. So if I inserted a 50 in my tree and there was nothing there yet, I would get a root node with 50 in it and then null child pointers, no children. All right, so here's the search part. If I now insert a 25, the rule for a binary search tree is that if you look at any parent, the child on the left has to be less than it, and the child on the right has to be greater than it. So this 25, because it's less than this root data, would become the child. And if I were to insert a 75, well, that has to go to the right of this root node. So the search part means that if you pick any node in a tree, to the left will be things smaller than it, to the right will be things greater than it. All right, now here's where it gets kind of interesting. If I were now to insert 15, where would that go? Once these links are established, you cannot rearrange them. So a 15 has to find a place on the tree that would be the proper ordering per the binary search tree rules, meaning that this has to be left of something that's greater than it. So the way this process works is you start at the root, and then you just move until you find an empty spot. So 15 would be less than 50, so the rule says I have to go to the left, which brings me here. But there's already something here. So now I look at the 15 and again I say, well, do I have to go to the left or I have to go to the right? In the case of 15, I have to go to the left, at which point I find a spot to put a 15. I will insert, let's insert a 65. Drawing pictures again, like I always do. Sometimes, though, when you're experimenting with a binary search tree, actually drawing the tree with its current contents helps a lot to kind of know what data is supposed to be where. These are going to seem like magic at first because it kind of makes sense right now, but watch how quickly it doesn't make sense, but it still follows the rules. So if I try to insert 65, I always start at root, and then I just go left, right, and left, right until I find a hole. So 65 is greater than 50, which means I have to go to the right because that's the rule, which brings me to 75. If I'm trying to insert 65, well, 65 has to be less than this, so I have to go to the left, at which point I find a place to hang the 65. Now, one thing that's interesting is that if you look at the 50, everything to the right of it is actually bigger than 50, interestingly enough, which has to be true. And if I go to the left of 50, everything to the left of 50 is less than 50, which is pretty crazy. Let's keep working on that. So I'm going to put a 68 in there. Let's just see where it goes, and then hopefully you mostly get the point. Okay, 68. So where does that go? Well, if we start at root, 68 is bigger than 50. So I go to the right, but I encounter something. That's correct. Ah, good question, Davis. Okay, so Davis asked what happens if they're the same, so I'm going to try one here in a second and answer that question. It's a very good question. So let me get 68 in there first. Okay, so 68, we start at root, we go to the right, but we come to 75, so 68 is less than that, so we have to go to the left. But now we find 65, so we have to go to the right, which means that we hang 68 down here. And if you notice, everything to the right of 50 is still bigger than 50. Okay, so the question was asked, what happens if I try to insert a duplicate? So if I try to insert 25, the answer is if I find 25 in here, then I don't insert it. So we will not allow duplicates in a binary search tree. We'll simply say, oh, I guess that's already there. So if it's not less than and it's not greater than, that means it's equal to, and we just will ignore it. So that's the answer to that question. So no duplicates. We could design it to allow duplicates, but we are not going to design. We're going to design ours to disallow duplicates. So these can get pretty hard to draw. I didn't plan this one out in terms of drawing it very well. But anyway, there's my tree after I did this series of inserts. So the shape of a binary search tree you cannot control. The shape of a binary search tree can be all kinds of different crazy things. It depends entirely on the data and the order in which it arrives. Now we'll see in a couple of weeks, removing data from a binary search tree is rough, is unpleasant work to do. But adding things or inserting things to a binary search tree is quite easy. And let's write this algorithm down. So the algorithm is going to look like this. In pseudocode. So whenever we're trying to insert something on a binary search tree, if we find a null, that's where we add the data. Go left, else if greater than, go right, and now I might ruin my whole good day of drawing. So when we're doing an insert, whenever we hit a null spot, then we are good to add a piece of data. If we're trying to add something that's less than where we're at, we go left. If we're trying to add something that's greater than where we're at, we go right. And there is one other possibility. So if it's not a blank spot and it's not less than and it's not greater than, the only other possibility is equal to, in which case we do nothing. Because we don't want duplicates. So that's kind of the rough, and I didn't draw that very pretty algorithm. Okay, I need to remember this tree so I can draw another picture of it. Mostly that is so you have a sense of how they get put together, and what they end up looking like is based on what order you added them in. So let me draw this one again and then sort of pick it apart. So 50, 25, 75, how high can I go? 50, 25, 75. I'm going to draw a little bit smaller here. Uh, 15 and then 65, 68. 15, 65, 68. Okay, so I'm going to draw a little bit smaller, and the reason I'm going to do that is because one thing that helps when you're writing code for a binary, this is root. One thing that helps when you are writing code for a binary search tree, root, get down here where we can see you. I can make this taller maybe. That didn't help a lot, but anyway. Anyway, where was I? Oh yeah, so I redrew this because one thing that is helpful is to be able to imagine a binary search tree is a whole bunch of trees sort of added together. So we have this sort of, this is the whole tree where the root is 50, but we can also imagine a tree, I hope you can, where the root is 25. We'd call this a subtree. Because in a sense, if you think about a family tree, parents and children have that same relationship. So I don't have any kids, but let's pretend that I do. So my parent had a child, and then if I had a child, so every node is potentially a parent to other children. And we call those subtrees. So if I pretended, for example, that 25 were the root, this is what its subtree would look like. Now, if I pretended like 15 were the parent, it would look like this, right? With no children. So if I looked at 25, it would have one child less than it. If I looked at 15 as a parent, it has no children. If I went to the right, 75, that subtree looks like this. If I go to 65 as a root, then it looks like this. And if I go to 68 as a parent, then its little subtree. So it can help to imagine a binary search tree as actually just being a whole bunch of subtrees connected together to form a larger tree. Right, like this might be my sister's family, this is me and my family, and my sister's children, and her children's children, and so on. Hopefully you can sort of picture that that is all of the different ways to sort of look at every node as if it were a parent of its own little tree. And the reason to do that is then to imagine if I were to insert at this point, let's say 10, whose child is it? So if I look at it from the grand tree, well, it's left to 50, left to 25, left to 15. Or I could look at this problem from the subtree and put it in here. Or I could look at the problem from this subtree and put it here. And once I've added 10, then it's now its own parent. It has no children to start, but it becomes its own subtree in its own right. The reason why we're going through this thought exercise is because we're going to use recursion a lot. And if you think about it, the problem of, and I say if you think about it, hopefully in the next 3 weeks, part of this will sink in. It's easy once you get it, and it's super, super hard until you do. But in terms of recursion, what a tree really is just smaller and smaller and smaller and smaller subtrees until you get to a null. So when you write algorithms on a binary search tree, you are trying to find the subtree. So, okay, it's this subtree. Okay, it's this subtree. Okay, it's this subtree, until you finally find a place where you can now create a new subtree connected to a parent. So that's sort of the whole algorithmic problem, is to reduce this tree to a subtree and a subtree and a subtree, and finally, oh, there's a place where I can make yet a new subtree, which is usually the point when we see null. Okay, so that's the drawing perspective. So you're going to see us write recursive algorithms that just keep sort of descending the tree until we find a blank spot recursively. Left subtree, left subtree, left subtree, null child. Okay, so that's the high level view. How do binary search trees work? Why do we call them that? And then prepare ourselves for lots of recursion. These are very easy to write recursively once you know how to write recursive functions, and that's the hard part, is writing those things. Okay, off with the picture. I think I can hide the browser for a second. So my first shot at this, what time is it? Okay, we're good on time. So first thing I'm going to do is just show you the node, which we're going to represent as a struct. And then I'm going to make a tree, and then I'm going to show you where the node goes in the tree, and then we'll go look at the lab code. So a node, what does that picture look like? Well, what it looks like is a pointer to the left, which we'll often refer to as the left child, although if you want to simplify it, just call it left. But for teaching purposes, I'm going to call it the left child. We're going to have a link or a pointer to a right child, and then we're going to have some data. Hopefully you're all comfortable with the idea of using the templated stuff. So this T is going to come from a template. And eventually I'm going to combine this into a binary search tree. Okay, so there's the tree. We also want a constructor because we like having nodes right at the start. Work quite nicely, but what you're going to see on the lab is, so here's what you're used to seeing. is this value equals value. So this is the parameter part, and then the nodes value, which you can see colored up. This left child equals null pointer. This right child equals null pointer. So you're used to seeing this setup. What you're going to see on lab is just something that I'm showing you so that you've seen it before. There's another way to write that constructor. And it looks like this. I'm going to use what's called an initialization list. This I would call a traditional constructor. But I'm going to just showing you this in the lab so that you've seen it and you've heard of it before. I'm going to use an initialization list this time. So if you'll notice, the block of code is empty, but with an initialization list, what you do is you take the various members, and notice how C++ is actually going to figure out that this is the node's value and this is the parameter. So in an initialization list, you take the fields and you initialize them in this list. So left child will be initialized to null pointer, right child will be initialized to null pointer. This is just an alternative syntax. There are places where this is very useful. We won't have them in our class, but if you ever do inheritance in C++, you'll see this again. So this is called an initialization list. It's simply an alternative to the traditional constructor. So on the lab code, you're going to see that I implemented the constructor in the initialization list style. It's all the same fields. It's all the same values. It's just not being done in the block. It's being done after this colon right here, which is what makes it an initialization list. You only use initialization lists with constructors, by the way. Okay, but you're going to see that in the code. Okay, so we also have and then I'm just doing this to separate it out so it's a little bit clearer. So we're going to have I like to call it the BS tree because I think it's funny, but binary search tree. But I also think it's funny. Public, private, you've seen this before. So in private, we are going to have a counter. I forget what we call it, size. The lab. Anyway, we're going to keep count. So this is the same thing, and I'm kind of relying on you understanding how linked lists work. The binary search tree is not the data. The nodes have the data. The binary search tree's job is to manage nodes. So it takes data, it creates nodes, it connects them to the tree. It retrieves data from nodes. It removes nodes. It prints out the contents. Same thing as a doubly linked list or a singly linked list, except for the way the structure ends up getting built looks different when we draw a picture of it. Okay, so they have a size, so the tree is going to keep a count of how many nodes do I own, and then it's going to have one pointer to a root node. And all I'm doing, just like we did before, there's no reason why I need this struct to be separate, so I'm going to just take it and put it in here, just like we did before. I don't need any of this garbage at the top. So this is already in your lab code. I just wanted you to be reminded about where it came from. So the struct definition is inside of the binary search tree class because it's the only place where we need it. It's going to share the T with the binary search tree as a constructor, and then we do this same trick. Some people would write it like this. We do the same trick where immediately upon declaring and defining this struct, we then declare a pointer to it called root. Okay, so that's that stuff. So let's go look at the lab and We'll just do a part of it today. Okay, this is all unit test. bstree.hpp. So the idea here is that bstree.hpp, we will build it this week in lab, we will build it more next week in lab, we may build it more the following week, but this is your data structure for your project. This will take the place of dlist.hpp. All right, but anyway, just to point out to you, here's the template, here's the class, here's the public section. It has a constructor for the tree, a destructor for the tree, a get size, a clear. In a binary search tree, since they're always sorted, there's no other way to build a binary search tree that's not sorted. There's only one way to add data in, which is the insert function. So we don't have a push root, we don't have a push child, we don't have push front, we have none of that, we just insert. And when we insert, the data goes to where it's supposed to go. And we have a printing function, which is where you'll see the first piece of magic. There's the size we were talking about. Here's the struct. I compressed the constructor for node here, but that's really just this that we looked at just a second ago. So it's a constructor with an initialization list. I called this data instead of value, so just pay attention to that. So here's the data field being initialized to new data. Here's the left child of the node to null, right child to null. Same thing, but except for I use the word data here and value in the other page. And then here's that whole root thing. There's a space in here, which is fine. Anyway, hopefully all of that's good. We also have some private functions, which we're going to deal with that here pretty quick in a second. But let's deal with the low-hanging fruit first. Let me bring up my camera again, and I'm going to smush it back. Okay, so binary search tree to start should be this. Right, it'll have a size of 0, and this root pointer will be at null because there's no nodes. So let's use the constructor to do that. Or I could do it this way instead. If I want to practice, I could use an initialization list on it. So the size will be 0, and the root will be null pointer. Just to practice the initialization list style again. So notice the block is empty because I used the initialization list instead to initialize those fields. Destructor, that's pretty familiar because we've done this before, this clear. Get size, that one's pretty obvious, so return this size, that one's easy. And the next thing that I recommend is let's stub out a few. So I just implemented the constructor. I just implemented the destructor, which just tells me to call clear, so I did. I just implemented get size. This is a template. Hopefully you have some practice on that from the last project in several labs. I haven't done clear yet, but it's a void returning function, so I can ignore that. I'm going to stub out insert. I'll just return false every time. I just want to get it to compile and see what's going on. That's a void returning function, so that's fine. If I go down here, there's more. So there's some private functions. Void ones I don't care about, but this bool, I need to return something to stub it out, so I'm going to do that. Then I'm going to go compile. So same deal as always, we only compile the CPP files. And then I'm going to run it with the -s option to see if I'm passing anything. Probably I'll get lucky and pass something. So the -s here is so that I can see all of the output from all of the tests. I do manage to pass a few, just getting lucky, so that's all right. In fact, I'm passing. I shouldn't even get to pass that many. But anyway, I'm passing some even though I've basically done nothing, although that suggests that maybe I did something right in the constructor. Okay, so now let's do a hard thing. And then we'll call it a day after this hard thing. Let me get my vertical camera back up. Okay, so we're about to, I just want this out of the way. I don't want to look at it. We're about to implement insert. And this is going to take a little bit of getting used to, but you may or may not remember with our singly linked list and doubly linked list, but we didn't have any functions that let any code in the outside world access head and tail. Every reference to head and tail was inside of the linked list class itself. And we want the same thing with root. So what we want to be careful with is that we only want references to root inside of the binary search tree class. The reason why we're doing that is because if another programmer used my tree as a library and we gave them access to root and they nulled it or moved it, they'd break all my algorithms. So we're going to protect root. The way to do that is to create pairs of functions. One is a public one. This is a public one. This is the one that that other programmer will call when they want to add. So they're just going to say tree insert 25. Now privately, what I'm actually going to do is return the result of calling my own private version of this function that needs to make a reference to root. This will take some getting used to, but I have this private, I'm in the private section, I have a private function that has references to root inside of it. And the reason I'm doing that is because I want that other programmer out there in the world to not have to look at root, touch root, mess up root, do none of that stuff. So third-party programmer, you just say insert 25, let me take it from there. So what I will do though is I will return the result of using my own private insert function, trying to insert the data starting at root. That third-party programmer, in theory, never has to see that truth. That to do an insert, I actually had to anchor it to root and start from there. I don't know if that makes sense. Hopefully it does. But that's why we have these pairs of functions, is because we want to be careful and let the outside world just not think about what is root. I don't know what root is. Just insert data and be done. Okay, so privately, I take that request to insert data and I pass it along to my own private insert function starting at root, the thing that I want to protect. I am returning that because an insert can fail on a duplicate. So you asked me to insert and tell you whether or not I did. I will return the result of my own private insert routine. Okay, so we already know part of this down here because if I call insert, we'll just do the same ones. If I call insert, say with 50, and the root is null, well, that's the spot to work. So this is a little bit different, and this is going to take some getting used to because you'll see this symbol right here. What the ampersand means in this context is that I already have a pointer inside the tree. So if you see that ampersand, what that should tell you is, oh, I'm already in the tree. If I were to take that off, what would happen on this insert is that I would end up with a different pointer. And I don't want that. I want the root pointer. And I'll draw this picture again in a second. But the reason the ampersand is there is because when I call insert with root, I want to be working with that pointer, not an external pointer. But I'll draw another picture in a second so you can see another example of that as we go. So the ampersand means when I get to, this is going to actually, of course, call insert 50 at root. My private function is actually using that actual root. And that's what the ampersand does. It's the actual root of the actual tree. Now the reason I want that is because I do not want to do this. I'm in the wrong function, aren't I? Yeah. I do not want this. The reason I don't want it is because I'm going to end up with temp $50. And you see this temp is just, it's not even connected. What a mess. So I don't want that. I don't want a temp. I want to take troot. In the private function, I call it troot. This is just like the current logo. Hopefully you'll get used to it. So I'm not going to do this at all. When I pass root, then what troot is the same as the actual root. So I'm going to take this troot, which is the actual root, that's the ampersand, and I'm going to make a node right there. So the beauty of this is that I don't have to figure out how to get root to point at it or do any extra work. It's just done. It's there. Done. Now I needed to do an if check there because that's only when troot is null that I want to do that. I have two other steps. So if I am looking at an empty spot on the tree, that's what troot really means. Oh, look, I have found a hole in the tree. I'm going to attach a node right to that blank spot in the tree. I also need to bump up the size, and then I will return true because I successfully attached a node to the tree. So let me start a new picture because I made a gross mess. Alright, so here's root. To start, it's null. And when I insert 50, that is privately going to call insert 50 at root. So the algorithm is literally going to receive literally root, and it's going to make a node right there because it was null. That's the easiest one. Now the hard ones. That's the if equals null. Okay, so now what happens if they do insert 25? Well, we know that privately we're going to call insert 25 and start at root, which is really the only place we ever have to start from. So if that happens, then this is troot. The function calls it troot. And it discovers, oh, I've already got data here, but this piece of data is actually less than. So what I need to do is take this troot marker and move it to be this one. So let's see how we do that. So if I don't find a hole, then I look to see if the new data coming in is less than the data that that pointer is pointing at. If that's the case, so if my 25 is less than this data, which is the case right now, then what I want to do is just restart the whole process, pretending like this is the root of the tree. So in other words, what I want to do is I want to insert that same piece of data, but I want to try that left child as the t root. So I'm going to take the t root from this one and I'm going to move it down to the left child of where I was at. Now in this case, when that happens, insert is going to come back in with 25 looking at here, and it's going to say, oh, that's null. I'm going to stick something right there. Pretty freaky. We didn't do everything that's required, so let's make sure that we do. So this is one of those weird recursive ones. It's calling the same function again, and it's relying on this recursive call to return a result. So the recursive call doesn't know the result will be just yet, so it's going to have to return whatever the recursive call is by resetting the whole sort of root of the function to the left. That's it. So now let's try insert 75. Which we know privately is going to try to insert 75 starting at the root. Okay, so t root will be here again. And since there's an ampersand, this passing in root with an ampersand, even though the function calls it t root, it means it's the same one. It's literally root. Crud, it's not null. And it's not less than, so we better check to see if it is now greater than. Then what we want to do is we want to reset the whole process at this point. So we're going to move t root to be here, just like we did when we went to the left. So I need to reset the whole process and start by trying to insert that new data to the right. And then I have to be careful here. Now if that happens, then t root for the function becomes this pointer, the right child, and that's null, so we can just attach the 75 to it. Pretty wild. We need to be careful here because the recursive call means that we don't know what the result's going to be, so we're just going to have to return the whatever the recursive call does and hope for the best. So what I will return will be the result of trying to reset the process down to the right. There is one other possibility. So let's draw a picture of it. The other possibility is that they try to insert, let's say, 25 again, which I know privately means that I'm going to call 25 and start at root. Okay, so 25 is now coming in, not null, and less than 50, so we're going to reset and try it as if this were the whole tree. Left child. This is now what we consider the root of the tree we're working in. 25 is not less than, so it's not null, it's not less than, and it's not greater than, which means it is a duplicate, and we don't want duplicates. And in that case, we're going to say no thank you. We're not doing that. What's crazy is that is the whole function. With some practice, that will make perfect sense, and it seems very elegant, just because the recursion just makes it work like magic. So the 25 is just going to say false, nope. This is going to return false. and then this is going to return false. Let's do another one, and then we'll sort of, I'll draw a trace. So let's do a what would be interesting. Let's do 35. Okay, so now let's do it as like a proper recursive function. So we're going to insert 35, and we're waiting for a result. But it makes a recursive call, so we're going to have to wait for the recursive call to return the result that then this function can return. The recursive call says, let's do 35 trying at the root, which we know to be 50, so I'm just going to write 50 in here. You probably can't see that at all. Yeah, you can't see that at all. It's terrible. I'm going to put a star next to it. That's pretty tiny. Maybe that's slightly better. I put a star 50 here because that's the one that I'm pointing at. This is the data. This is the one that I'm pointing at. So the check is it null? No. Is 35 less than? Yes. So I'm going to have to wait for my result to return. So what I return is going to be whatever happens when I go to the left. So what happens when I go to the left? Well, to the left is trying to insert the data 35, and I'm going to be looking at 25 when I go to the left. Now it's going to say, is that null? Nope. Is it less than? Nope. It is greater than. So this result has to wait until this call happens, which is a 35 and nothing right here. So at that point, we connect a node up for that data. We increase the size, and we return true. And now this cascade happens. So, oh, you return true. That's what I get. And then I will return true. And then I will return true. And then my third-party programmer gets a true back. Ah, my 35 went in the tree. Pretty crazy how that works. And it's a lot of work, meaning the computer and the data structure do a lot of work for very little code. Let's compile that. That'll probably be the last thing that we do. Let's compile it and see if it works. In theory, we may or may not pass more tests. I'm not going to be too worried if we don't, but we might. I didn't even look the last time. What did I pass the last time around? Oh, I cleared the screen. It doesn't matter. But I'm passing 15 assertions and failing 4. So that's actually, most of them are passing now. That's pretty wild. So let's see which ones do pass. Here's the empty tree. Passes without a problem. Here's a tree where I just put one thing in it. The only thing it's failing is part of the printing. Here's a passing where it tries to insert a duplicate value. Printing failing. Size passes. Inserting a duplicate fails, inserting a duplicate fails, inserting a duplicate fails, duplicate fails, duplicate fails. So that's all good. Those are all duplicates, and they all fail because they shouldn't allow duplicates. Size still 7. This is after a clear because we're not doing that yet, I would assume. Anyway, where does that leave us then? So we need to do clear and printing, which we'll do on Thursday. These are hard. This is a hard data structure. It's got recursion. That makes it harder, probably, than the linked lists because those did not use recursion. takes getting used to. We're going to walk through every algorithm together, so hopefully somewhere in there it will help you to start making sense of it. Draw pictures. Mostly make sure that you can draw a proper picture of the structure so that you know where the data should be. Um, if you can learn how to draw pictures of recursion happening, that can help. So each one of these boxes is a recursive call that stacks up on another recursive call that then has to wait until the ones above it release. That's what that is. So this is the original call, a recursive call, a recursive call, a recursive call. Technically this one isn't, but we'll call it that. That have to wait until an actual result is produced, and then the whole stack can unravel to a result. So if you can learn how to draw those pictures, that helps a lot as well. Okay, I'm going to wait around for a couple minutes and answer questions if there are any. Otherwise, I'm done for the day. I will be here tomorrow at 10, as always. To answer questions, that's usually pretty lonely. We've only got 3 weeks for this project, so don't let that one sit too long before you start building up your driver. You're going to get most of the rest of the code in the labs over the next few weeks, so worry about the driver if you're trying to get started. Thank you. Appreciate it, Jake. And have a good couple of days in the meantime if I don't see or hear from you before 2 on Thursday, or 11. We're 11 a.m. 11 a.m. on Thursday is when we'll be back to finish this lab. Thanks. You too, Toby. See you next time.